Good evening, ladies and gentlemen. How are you all doing? So I see class participation is very low this evening, so I assume it's a combination between load shedding that has just started and semester tests happening this week. I'm also well, thank you. Am I correct in saying you guys have written the test on Saturday? And I assume that was, if I'm correct, that is one of your math modules. Stats, how did it go? Why poor? I know back when I had stats, that was probably one of my most difficult subjects, so I understand. And yeah, studied a lot of calculus. That was, and I can assure you that is a better choice because if you fail stats, then it shouldn't hold up the rest of your other modules. But if you fail calc, then you are blocked from a hell of a load of other modules as well. So I just want to say thank you to you guys that's always attending my classes. It really means a lot. So I can see I'm going frequently through this of who's online, and it's the regular group. So I want to say thank you very much for being in my class. It really means a lot to me and I really appreciate it. And that also means I was planning on giving in quotes, wanted to preach to you guys in quotes tonight, but I'm going to be preaching to the choir and the wrong part of the group, so it doesn't help preaching to you guys. But hopefully, everyone watching the recordings will get a point. So, the first point I want to make is all relevant information to this course is in the study guide. All relevant information is on the announcements, on WhatsApp, on Discord, and I try to send out emails for every announcement as well. And then there's still students asking questions, when is the assignment due? Read the assignment guide. And the students that emailed me today and sent me messages today, what should they do for the assignment? It's now starting to become very late to do the assignment. So that is quite shocking to me. If you haven't started the assignment yet, and has been up since February. So that is just a warning to everyone. Don't underestimate the assignment. And also, all relevant information is online everywhere. Then secondly, for the assignment, plagiarism is a serious matter. And plagiarism won't be entertained anywhere on university level. So, to give you a heads up, let me ask, have you guys used Turnitin before? Okay, so you guys are familiar with it. So, used what? Turnitin. So let me type it out in the chat. So Turnitin. So for those of you that's not familiar with Turnitin, it checks for plagiarism. So one thing that Turnitin also does is, I don't know if you guys are familiar with it, but it keeps a repository of all assignments submitted. So even if it's the same assignment as the year before, it checks your assignment to the years before's assignment to make sure you haven't copied from the year before as well. So university rules is If you have a similarity report of 30% or less, then you're fine. If you're above 30%, then you are in big trouble. Some faculties and departments can change a little bit to make it even less. But for our course, 30% is fine, and I won't, what's the word I'm looking for? Entertain plagiarism. So that's why I'm giving you a link that you can use. It's already open over and over with, that you can check for plagiarism. And then there's a final submission link as well. So if you are caught plagiarizing something, or if your plagiarism report is above 30%, I will give it over to a disciplinary committee and they will deal with you, where punishment can be expelled from university, and you won't be allowed to register at any tertiary institute internationally for 2 years. So will it think we copy ourselves if we submit the same thing twice? So it won't. So that's a setting I have disabled and turned it in, so it won't. And then our last part of the admin I want to ask you guys, is there anyone that wants a face-to-face consultation tomorrow on campus? Because now on WhatsApp, there's these students that messaged me that want face-to-face consultations. But I want to ask if there is someone else, because if it's only 2 students, I can try and reschedule and make it virtual, because I have work to do at the observatory. But if you guys want to see me on campus, then I will be on campus tomorrow. So if I'm on campus tomorrow, I will be there probably from 9:30 to about 2:30. Okay, cool. So that's consensus with that. Then I will be on campus tomorrow for consultation. So do you guys have any questions on the previous work we have done so far? Okay, cool. So tomorrow night's lecture, the first couple of minutes, I will go through the memos of both quizzes. We haven't done that, so I will do that in the first 10 minutes of tomorrow night's class. So does differentiation count? So what's happening with differentiation? Where are you guys struggling with differentiation? So what does a quasar look like? I always thought it was a supermassive black hole, but I guess it isn't. So if you think about a quasar, so the quasar is a, think about it as the nucleus of a galaxy, so active galactic nuclei. So in optical pictures, it will look like a super bright star. So it looks like a star that is very close to Earth, but in fact, it is the active galactic nuclei of a distant galaxy. So that is what it will look like in an optical telescope. Through radio telescopes, depending on what frequency you are observing, it can be extremely bright in radio waves, extremely bright in X-rays, and extremely bright in gamma rays, but usually it will be around about X-rays. So yes, the quasar includes the black hole. So it includes the black hole, it includes the event horizon, so it includes everything in the nucleus of the galaxy. Okay, cool. So Mr. Pretorius, x to the power y and y to the power x. So with calculus, how do you guys prepare for your tests and exams? Practice past papers. all the worksheets and a bunch of questions from the handbook, past papers, practice makes perfect. So you guys actually use the questions at the back of each chapter in the textbook. Okay, so one piece of advice I can give you with practicing with past papers, especially in calculus. So it can be that the calculus lecturer changes in the following year or so, and then a new lecturer will have a different way of asking questions. So the past papers isn't a clear and the best way to prepare for your tests and exams. Although it's very good practice, it's not the best way. So the best way would be that's what I usually do. So the end of your textbook, the questions you have, end of each chapter, end of each section, try and practice as much of those as possible. So let me ask, you guys have access to the solutions manual of the textbook? So that helps if you have the solutions manual of textbook, and if you know where to look online, you can actually find it, especially on a few torrent sites and a few Bookshare sites. Let's get to tonight's lecture. So far on this course, we have discussed stars. We discussed how stars were formed. We classified different stars. And like the analogy said, we created a family portrait of stars. How to classify stars, what happens when they die. We've learned when a star dies about white dwarfs. We learned about neutron stars. We learned about black holes. We learned about the galaxy and how our galaxy formed. We learned about different galaxies. And we touched on cosmology, so how the universe began and how the universe is evolving and expanding. But that leaves out a few pieces. And can you guys guess what pieces are we still missing? So now we're going to zoom from tonight's lecture and last couple of lectures we have. We're now going to zoom into more smaller detail. So yes, Mr. Mel, correct. The solar system, extrasolar planets. So now we're going to look at our solar system in general. How does our system form? How do the different planets form? What planets are our solar systems? What is the characteristics of the planets in our solar system? Are there planets around other stars? What are the characteristics of those planets as well? And then we're going to look at asteroids and comets. What makes an asteroid and a comet a comet? How do they originate? Where do they come from? And then finally, we're going to end off this module in a couple of weeks with the theory of extraterrestrial intelligence. But for tonight, we're now going to start about the origin of our solar system and what is extrasolar planets. So for this lecture, we're going to look at the great chain of our origins, the survey of the solar system, the story of planet building, and is the planets orbiting other stars. So what can you guys tell me about our own solar system? Yes, we have 8 planets. Definitely has 9 planets. So what do you guys say? Is Pluto a planet or not? Why do you guys say no? The smart people say it's not, so it's not got emoted. So that is where I differ a bit from the rest of the astronomy community. I still believe that Pluto should be kept as a planet, but the only reason is due to tradition. But the majority of the astronomical community decided that Pluto does not meet the criteria for a planet, and it was demoted to a planetoid. I basically still believe it's a planet, but that's what the international community decided, and the majority vote was, and the definition was, so that is what we're dealing with now. But what else can you tell me about a solar system? So we will deal in the following lectures of what a dwarf planet is and the definitions of planets. So here is a nice overview of our solar system. So the Oort cloud always seemed like an interesting place. Yes, we will discuss the Oort cloud as well. You have studied the appearance, origin, structure, and evolution of stars, galaxies, and the entire universe. So far, though, your studies have left out one important type of object, planets. Now it is time for you to fill in that blank. In this chapter, once you learn the evidence of how star systems formed, you can understand how the process you have been studying produced Earth, your home planet. And because thousands of planets have been discovered around other stars, you can be confident that those processes are not unique to our solar system. As you explore our solar system in space and time, you will find answers to four important questions. What are the observed properties of the solar system as a whole? How does the solar system form? How do planets form? What do astronomers know about other planetary systems? Question, sir, hypothetically speaking, what would happen if the moon crashed into Earth? So that is a very, very good question. So hypothetically, Earth would survive the collision, but life on Earth would not survive the collision. I know there is a calculation, I don't know the value by heart, but if an object of a certain size and density hits Earth, then it will be an extinction level event like the dinosaurs. So if the moon hits Earth, that will be a catastrophic extinction event. So Earth will survive, yes. Earth will be deformed, but life as we know it won't survive further on Earth. So if you think about our own solar system is not just the planet. Our solar system are an intriguing object. So if we look at our solar system, there's an asteroid belt between Mars and Jupiter. And here we can see is the inner solar system. Here we can see the inner epsilon system, so the inner asteroid belt. Then going out past Neptune, there's another asteroid belt called the Kuiper belt. And then behind Pluto and the dwarf planets, we have the Oort cloud, also the Oort cloud, the comet belt, and the Oort cloud as well. And all of these are important aspects of our solar system that we are going to discuss. So you can study the solar system for many reasons. You can study Earth and its sibling planets because, as you're about to discover, there are almost certainly more planets in the universe than stars. Above all, you can study the solar system because it is your home in the universe. Because humans are an intelligent species. We have the ability and responsibility to wonder where we are and what we are. Our kind have inhabited the solar system for at least 100,000 years. but only with the last few hundred years have we begun to understand what a solar system is. You are linked through a great chain of origins that leads backward through time to an instant when the universe began, 13.8 billion years ago. The gradual discovery of the links in that chain has been one of the most exciting adventures of human intellect. In earlier chapters, you studied some of that story. The origin of the universe in a Big Bang, the formation of galaxies, the origin of stars, and the growth of the chemical elements. Now we will explore further to consider the origin of planets. We're going to start this lecture with the history of the atoms in your body. So the universe began in a Big Bang. By the time the universe was a few minutes old, the protons, neutrons, and electrons in your body had came into existence. You are made of very old matter. Although those particles formed quickly, they were not linked together to form many of the atoms that are common today. The matter in the early universe was about 75% hydrogen and 25% helium. Although your body does not contain helium, it does contain many of those ancient hydrogen atoms, unchanged since the universe began. Evidence indicates that almost no atoms heavier than helium were made in a Big Bang. Within a few 100 million years after the Big Bang, matter began to collect to form galaxies containing billions of stars. We have learned that nuclear reactions inside stars are where low-mass atoms such as hydrogen are combined to make heavier atoms. Generations after generation of stars cook the original particles, fusing them into atoms such as carbon, nitrogen, and oxygen that are common in your body. Even the calcium atoms in your bones were assembled in stars. Massive stars produced iron in their cores, but much of that iron is destroyed when a core collapses and the star explodes as a supernova. Most of the iron on Earth and in your body was produced instead by carbon fusion in type 1a supernova explosions and by the decay of radioactive atoms in the expanding matter ejected by type 2 supernovae. Atoms heavier than iron, such as gold, silver, and iodine, are created by rapid nuclear reactions that can occur only during supernova explosions. Iodine is critical to the function of your thyroid gland, and you probably have gold and silver jewelry or dental fillings. Realize that these types of atoms, which are part of your life, on Earth, were made during the violent deaths of massive stars long ago. So that comes in with, like Carl Sagan said, we are all made of star stuff. And it also comes down to the conservation of matter. So matter cannot be created or destroyed, but can only be transferred from one form to another. So our galaxy contains at least 100 billion stars, of which the sun is one. Astronomers have a variety of evidence that the sun formed from a cloud of gas and dust about 5 billion years ago, and the atoms in your body were part of that cloud. The stories of how the cloud gave birth to the planets and how the atoms in your body found their way onto Earth and into you make up the story of this chapter. As you explore the origin of the solar system, keep in mind the great chain of origins that created the atoms. As the geologist Preston Cloud remarked, stars have died that we might live. So how many slides are there in this lecture about 9 planets? So in this lecture slides we have 122 slides, and then we will discuss in the following lectures the planets on their own. Firstly, we're going to look at the solar nebula theory. So over the last 2 centuries, astronomers have proposed 2 kinds of hypotheses for the origin of planets in our solar system. The catastrophic hypothesis proposed that the planets formed when some improbable event, such as the collision of the sun and another star. The evolutionary hypothesis proposed that the planets formed gradually and naturally as the sun formed. Since around the middle of the 20th century, evidence became overwhelming for the evolutionary scenario. In fact, The evolutionary hypothesis is so comprehensive and explains so many of the observations that it can be considered to have graduated from being just a hypothesis to being properly called a theory. Today, astronomers are continuing to refine the details of that theory. So what is the solar nebula theory? So the solar nebula theory supposes that planets form in a rotating disk of gas and dust around young stars. So in this image, we can see a representation of how this happens. So a rotating cloud of gas contracts and flattens around the star to become a thin disk of gas and dust around the forming sun at the center. Planets grow from gas and dust in the disk and are left behind when the disk clears. So you've seen clear evidence that disks of gas and dust are common around young stars. Bipolar flows from protostars were the first evidence of such disks. But modern techniques can image the disks directly. The evidence is strong that our own planetary system formed in such a disk-shaped cloud around the sun. When the sun became luminous enough, the remaining gas and dust were blown away into space, leaving the planets orbiting the sun. Many of the young stars in the Orion Nebula are surrounded by disks of gas and dust, but intense light from the brightest star in the neighborhood is evaporating the disks to form expanding clouds of gas. These peculiar disks may evaporate before they can form planets, but a large number of such disks show that planet construction material around young stars is common. According to the nebula year theory, Earth and the other planets of the solar system formed billions of years ago as the sun condensed from a cloud of interstellar gas and dust. If planet formation is a natural part of star formation, most stars should have planets. To test the hypothesis about the solar system was born, astronomers searched the present solar system for evidence of its past. In this section, you will survey the solar system and compile a list of its most significant characteristics that are potential clues to how it formed. You can begin with the most general view of the solar system. It is, in fact, almost entirely empty space. Imagine reducing the scale of the solar system until Earth is the size of a grain of table salt, about 0.3 millimeters in diameter. The moon is a speck of pepper about 1 centimeter away, and the sun is the size of a small plum located 4 meters from Earth. Jupiter is an apple seed 21 meters from the sun. Neptune, at an edge of the planetary zone, is a large grain of sand more than 120 meters from the central plum. Your model solar system would be larger than 2 football fields and would need a powerful microscope to detect the asteroids orbiting between Mars and Jupiter. The planets are tiny specks of matter scattered around the sun, the last remains of the solar nebula. The planets revolve around the sun in orbits that lie close to a common plane. The orbit of Mercury, the closest planet to the sun, is tipped 7 degrees to Earth's orbit. The rest of the planet's orbital planes are inclined by more than 3.4 degrees. As you can see, the solar system is basically flat and disc-shaped. The rotation of the sun and planets on their axis also seem related to the rotation of the disk. The sun rotates with its equator inclined only 7.2 degrees to Earth's orbit, and most of the other planets' equators are tipped less than 30 degrees. The rotations of Venus and Uranus are peculiar, however. Venus rotates backward compared with the other planets, whereas Uranus rotates on its side with its equator almost perpendicular to its orbit. You will explore these planets in detail in chapters 17 and 18, but later in this chapter you will be able to understand how they might have acquired their peculiar rotations. There is a preferred direction of motion in the solar system, counterclockwise, as seen from the north. All the planets revolve around the sun in that direction, with the exception of Venus and Uranus. All the planets also rotate on their axis in that direction. Furthermore, nearly all of the motions in the solar system, including Earth's moon orbit around their respective planets, in that same direction, with only a few exceptions. Revolution and rotation in the solar system follow a single theme. Apparently, these motions today are related to the original rotation of a disk of a solar system construction material. So a bit off topic. So if you ever see people who were on an ice skate ring, what direction are you skating in? Any ideas? Yes, you skate in a counterclockwise direction. So, taking athletics as an example, if you sit on the in a stadium and you look at the athletics track, which way does the athletes run around the track? Also counterclockwise. And if you look at American NASCAR, which way do they drive around the track? Yes, also counterclockwise. So I have no idea why on earth people choose counterclockwise. So ice skating ring, athletics, NASCAR. I have no idea why everything is counterclockwise. So that is something our psychology friends can answer. But in nature, depending on what happens, so if you look at a planet, that's counterclockwise. So maybe it's tradition. That could be tradition. So is there some weird coincidence? Yes, that is a weird coincidence. So I don't have an answer to this question. So this has to do more with the psychology of people and tradition. And it could be a few other factors as well. But rotation in space is usually counterclockwise. So will this finally answer my long-lasting question of why Venus rotates longer than its revolution? Yes, it will. So why don't clocks go counterclockwise then? That is because the person or people of civilizations that invented the clock chose a direction and it stuck that way. So that's just something interesting to think about. So as the heart is on the left-hand side for humans and animals, running anti-clockwise makes the centrifugal force in the body to act from a left to a right, whereas it is from right to left for clockwise running. Racing tracks, animal shows, and circuses wheels almost have only left turns. Isn't because the Earth is a bit tipped in a counterclockwise direction, so naturally our bodies prefer moving that way. That could be, I have no idea, but that's just something for you guys to think about. So there are two kinds of planets in our own solar system. So perhaps the most striking clue to the origin of the solar system comes from the obvious division of the planets into two groups, the small Earth-like worlds and the giant Jupiter-like worlds. The difference is so dramatic that you are led to say, aha, this must mean something. So notice three important points and learn two new terms with these. So firstly, the two kinds of planets are distinguished by the location. The four inner terrestrial planets are quite different from the four outer Jovian planets. Craters are common. Almost every solid surface in the solar system is covered with craters. And thirdly, the two groups of planets are also distinguished by properties such as the number of moons and presence or absence of rings. The theory of the origins of the planets needs to explain those properties. Can everyone still hear me? Okay, so load shedding is causing havoc on my side. I assume my connection will be stable now. So, speaking about this, is from here on we are going to distinguish the planets into the terrestrial planets. So that is the four innermost planets, and into the terrestrial, the Jovian planets, that is the Jupiter type planets. So the division of the planets into two groups is a clue to how our solar system formed. The present properties of individual planets, however, don't tell everything you need to know about their origins. The planets have all evolved since they formed. For further clues about the origin of planets, you can look at smaller objects that have remained largely unchanged since soon after the birth of the solar system. The Sun and planets are not the only products of the solar nebula. The solar system is littered with several kinds of space debris such as asteroids, comets, and meteoroids. These objects will be considered in further detail in Chapter 19, but they are mentioned here because they are a rich source of information about the origin of the planets. The asteroids, sometimes called minor planets, are small rocky worlds, most of which orbit the Sun in a belt between the orbits of Mars and Jupiter. More than 100,000 asteroids have orbits that are charted. It is a common misconception that asteroids are the remains of a planet that broke apart. In fact, planets are held together very tightly by their gravity and do not break apart. Astronomers recognize the asteroids as debris left over from a failure of a planet to form, at a distance of about 3 AU from the Sun. So it is hard to start, but when you get going, then it gets easier. Well, I'm assuming. What are you guys discussing in the chat? Oh, the assignment. You guys have any questions about the assignment? Okay, so let's continue on with the lecture. So spectroscopic observations indicate that asteroid surfaces are made up of a variety of rocky and metallic materials. So, sir, do you have a good website that takes active moon photos? So, not a website, but I have a few colleagues that actually take a good photos. No, it's not necessary to get a high vantage point, but it can help. But no, it's not necessary. In case the clouds kill me again, so if the case clouds, you can use software that can help you, such as Stellarium. And I can ask tomorrow, that is also fine. So note that metal is used here in a familiar sense, referring to substances such as iron rather than the stellar astronomer's sense, meaning by element heavier than hydrogen and helium. Photographs returned by robotic spacecraft show that asteroids are generally irregular in shape and covered with craters. Those observations will be discussed in detail in Chapter 19. But in this quick survey of the solar system, you have enough information to conclude that the solar nebula included elements that composed rock and metal, and also that collisions have played an important role in the solar system history. So should we take panoramic photos in case the moon shifts by a significant amount? So that is up to you. As long as I can see the phase of the moon as well as the location of the moon, then everything is fine. So, sorry sir, what did you say the name of the software is that I can use for some moon photos? It's called Stellarium. Pleasure. So here we can see in image A, over a period of 3 weeks, the NEAR spacecraft approached the asteroid Eros and recorded a series of images arranged here in an entertaining pattern showing the asteroid's irregular shape and 5-hour rotation period. Eros is 34 kilometers long. In image B, this close-up of the surface of Eros show an area about 11 kilometers from the top to bottom. Since 1992, astronomers have discovered more than 1,000 small, dark, icy bodies orbiting the outer fringes of the solar system beyond Neptune. This collection of objects is called the Kuiper Belt, after astronomer Gerard Kuiper, who predicted their existence in the 1950s. There are probably 100 million objects larger than 1 kilometer in the Kuiper Belt, many more than in the asteroid belt. A successful theory for the formation of the solar system should also explain how the Kuiper Belt objects, KBOs, came to be where they are. You'll find out more about the origins of the Kuiper Belt in Chapter 18. So, question, sir, can I take separate photos of the position of the moon and higher quality, more zoomed in ones separately, and just specifically which close-up is linked to which position? Yes, you're more than welcome to do that as well. So here we can see is the Sun, Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, here's Pluto, here's Aries, and here is the Kuiper Belt. So a good sci-fi series to watch that put everything into perspective is, what is his name again? Now name escaped me. So this is just an interesting topic to me, but do you think asteroid mining will happen in the near future? Yes, that will actually happen in the near future. So there are actually research groups being set up to investigate this. And I know some of the biggest mining companies, I know De Beers is De Beers and Anglo American has already set up think tanks to investigate asteroid mining. So yes, that will happen. Elon Musk of SpaceX is also investigating asteroid mining. So yes, that is going to happen. So currently we are on a new space race. So the first thing is to get to the moon again and then to Mars. But beyond Mars is to get to an asteroid. And then how can you mine the asteroid and get samples back to Earth? Or even set up a mining facility. That asteroid, the name of that series I was thinking about is called The Expanse. And in The Expanse, they also do asteroid mining. But yes, that will happen. So if we put everything together, this is also a view of what our solar system looks like with the Kuiper Belt. So in contrast to the rocky asteroids and dark Kuiper Belt objects, the brightest comets can be seen with the naked eye and are impressively beautiful objects. A comet may be visible for many weeks as it sweeps through the inner solar system. Most comets are faint, however, and difficult to locate even at their brightest. So nuclei of comets are ice-rich bodies a few kilometers, tens of kilometers in diameter, similar in size to asteroids. Like asteroids, comets are understood to be left over from the origin of the planets and provide evidence that at least some parts of the solar nebula had ambient icy material. You will discover more about the composition and history of comets in Chapter 19. So what do you reckon the asteroid mining will mostly be used for? Jewelry, fuel? So that is actually very, very good. So as you guys have probably realized and noticed is that, especially when we talk about in astronomy context, that heavy elements such as gold, silver, does not originate naturally on Earth. So once they are finished with the gold reserves on Earth, for example, that is done and there's no more gold. But as the asteroids formed, and same way at the same time the Earth is formed, there are still these rare metals in asteroids as well. So now the asteroid exists. I'm not sure about its value, but I know in the asteroid belt between Mars and Jupiter there is an asteroid, and its value is sitting somewhere at $1 trillion. So if you can mine it, you will make a lot of money off it. But the problem is how to get there and how to get the material back to Earth. And then from that material we find, you'll make jewelry, you'll make different things we use on Earth. So do you think space litter from NASA and stuff are a hazard to us? Yes, space litter is an extreme hazard to us. So if you look at different satellites' orbits, a lot of the orbit space are filled with space junk. So that means satellites are not being used before, rocket boosters that was left up there, parts from rockets that are still up there. So yes, that is a big problem. And if one of those fragments hit another satellite, that satellite can become destroyed. So there is a theory called the Kessler effect. Are you guys familiar with the Kessler effect? So the Kessler effect says there's so many space debris and space junk in orbit. If the wrong object hits the satellite or a different piece of space rubble, it can cause a chain reaction. So one object will hit another object, that will hit another object, that will hit another object, and then ultimately everything in orbit will be destroyed and knocked out. And that is the Kessler effect. And that is something that is actually becoming quite a real possibility. So the nuclei of comets are ice-rich bodies a few kilometers or tens of kilometers in diameter. Similar to the size of asteroids, like asteroids, comets are understood to be left over from the origin of planets and provide evidence that at least some parts of the solar nebula and abundant icy material. So you will discover more about the composition and history of comets in Chapter 19. So then we are trapped on Earth and can't launch rockets because we will hit by junk. No, so the thing is, the Kessler effect is everything will be knocked out of orbit and everything that's in orbit will be destroyed in orbit. So that means all our GPS satellites has to be reconstructed, relaunched again, and that will cost a hell lot of money. So comet nucleus remains frozen and inactive while it is far from its sun. If the comet's orbit carries it into the inner solar system, the sun's heat begins to vaporize the ices, releasing gas and dust. The flow of solar wind pushes radiation pressure exerted by sunlight
pushes the gas and dust away, forming a long tail. As a result, the tail of a comet always points approximately away from the sun. No matter what direction the comet itself is moving, the beautiful tail of a comet can be longer than an AU for its produced by a relatively tiny nucleus, only a few kilometers in diameter. So this could be a good question for this exam, is which way does the tail of a comet point? So here we can see an image of a comet may be visible in the evening or morning sky for weeks as it moves through the inner solar system. Although comets are moving relatively rapidly along their orbits, they are so distant that on any particular evening, a comet seems to hang motionless in the sky. So comet Hyakutake is shown here near Polaris in 1996. Then image B. A comet in a long elliptical orbit becomes visible when the sun's heat vaporizes its ice and pushes the gas and dust away in a tail pointing away from the sun. Yes, so this is the tricky. So what's happening here is that's a photograph taken of the comet, but we call these star trail images. So remember, the Earth is spinning around its own axis. So this is the spinning of the axis that is being noticed. Imagine just chucking a really powerful electromagnetic orbit to gather all the junk. So there's actually now an idea proposed to use a giant laser to push the space junk out of orbit or have them deorbit. So the idea is that you push the laser towards these objects and you just deflect them or move them a few millimeters so that the orbits change, so they go into deep space or that they fall back to Earth and burn out in the atmosphere. So unlike the stately comets, meteors flash across the sky in momentary streaks of light. They're commonly called shooting stars. Of course, they are not stars, but small bits of rock and metal colliding with Earth's atmosphere and bursting into incandescent vapor because of friction with the air about 80 kilometers above the ground. This vapor condenses to form dust that settles slowly to Earth, adding about 40,000 tons per year to the planet's mass. So I'm sure you guys have seen a meteor before. So in this image, we can see a sudden streak of glowing gas produced by a bit of material falling into Earth's atmosphere. Friction with the air vaporizes the material about 80 kilometers above the Earth's surface. This meteor is seen against the background of the Milky Way. So if you are in a very dark place, you should be able to see between 20 and 30 meteors per minute. If you are in a more suburban area, then you should be able to see between 2 and 4 meteors per minute. Technically, the word meteor refers to the streak of light in the sky. In space, before it's a fiery plunge, it is called a meteoroid. And any part of that survived its firing passage to Earth is called a meteorite. Most meteoroids are specks of dust, grains of sand, and tiny pebbles. Almost all the meteors you see in the sky are produced by meteoroids that weigh less than 1 gram. Only rarely a meteoroid massive enough and strong enough to survive its plunge and reach Earth's surface. Thousands of meteorites have been found, and you will learn more about their specific types in chapter 19. Meteorites are mentioned here for one specific clue. They can give you concerning about solar nebula. Meteorites can reveal the age of the solar system. So yes, that's a lot. So if you ever are patient enough and just sit outside, you are supposed to see them. So we are scientists and we like to name stuff to understand what they are. So, Mr. Marvel, so if you see a meteor shower, you will see, because they usually estimate it to make it easier for people to understand and to know what the expectation is, they usually measure it in how many you see per hour. So depending where you are on Earth, how dark it is in consideration. But usually the average for a good meteor shower is around about between 12 and 20 meteorites per hour. I understand, but if you're in a dark place, you should be able to see quite a few per hour. According to the solar nebula theory, the planets should be about the same age as the Sun. The most accurate way to find the age of the rocky body is to bring a sample into the laboratory and realize the radioactive elements it contains. When a rock solidifies, it incorporates known percentages of the chemical elements. A few of these elements have forms called isotopes, so look back to chapter 6, section 1, that are radioactive, meaning they gradually decay into other isotopes. For example, potassium-40, called a parent isotope, decays into calcium-40 and argon-40, called daughter isotopes. The half-life of a radioactive substance is the time it takes for half of the parent isotope atoms to decay into daughter isotope atoms. So you guys happy with what is meant with isotopes? Awesome. The abundance of radioactive substances gradually decreases as it decays, and the abundances of the daughter substances gradually increase. The half-life of potassium-40 is 1.3 billion years. If you have information about the abundance of the elements in the original rock, you can compare those with the present abundances and find the age of the rock. For example, if you study a rock and find that only 50% of the potassium-40 remains, and the rest has become a mixture of daughter isotopes, you can conclude that half-life must have passed and that a rock is 1.3 billion years old. So here in image A, we can see the radioactive parent atoms in red. In a mineral, sample decay into daughter elements in blue. So half the radioactive atoms are left after one half-life. After a fourth after two half-lives, an eighth after three half-lives, and so on. Then in image B, radioactive dating shows that this fragment of Allen meteorite is 4.56 billion years old. It contains a few older interstellar grains, which formed long before our solar system did. Potassium isn't the only radioactive element used in radioactive dating. Uranium-238 decays with a half-life of 4.5 billion years to form lead-206 and other isotopes. Rubidium-87 decays into strontium-87 with a half-life of 47 billion years. Any of these substances can be used as radioactive clock to find the age of mineral samples. Of course, to find a radioactive age, you need to get a sample in the laboratory. And the only celestial bodies of which scientists have samples are Earth, the Moon, Mars, and meteorites. The oldest Earth rocks so far discovered and dated are tiny zircon crystals from Australia that are 4.4 billion years old. That does not mean the Earth formed 4.4 billion years ago. As you will see in the next chapter, the surface of Earth is active and the crust is continuously destroyed and reformed with material welling up from beneath the crust. Although no one has yet been to Mars, over a dozen meteorites found on Earth has been identified by the chemical composition as having come from Mars. Most of these have ages of only a billion years or so, but one has an age of approximately 4.5 billion years. Mars must be at least that old. The most important source for determining the age of the solar system is meteorites. Radioactive dating of meteorites yields a range of ages, but there is fairly precise upper limit. Many meteorite samples have ages of 4.56 billion years old, and none are older. That figure is widely accepted as the age of the solar system and is often rounded to 4.6 billion years. The true age of the Earth, Moon, and Mars are also assumed to be 4.6 billion years. Although no rocks from those bodies have yet been found that are remained unaltered for that entire stretch of time. So on this note, you will find some conspiracy theorists that says, no, you can't determine the age of the Earth. No, you can't determine the age of the universe. And carbon dating and radioactive dating is wrong. They are speaking crap. This is the most accurate way to determine things, and it is scientifically proven. So if someone tells you no, it's not so, you can say, but it is, and here is the evidence. And the evidence comes from astronomy. One last, have we found any interstellar asteroids on Earth? Not on Earth, but we have seen a few interstellar visitors going through our solar system. One last celestial body deserves mention, the Sun. No, we have not taken samples from interstellar objects, but we have seen a few of them. I just always find entertaining to listen to conspiracy theorists. It's like watching zoo animals go about their day. Yes, that is very true, and it can become quite ridiculous at some times. So astronomers estimate the age of the Sun to be about 5 billion years. But that is not a radioactive date because we have no samples of radioactive material from the Sun. Instead, an independent estimate for the age of the Sun can be made using helioseismological observations and mathematical models of the Sun's interior, so remember from the earlier chapters. This yields a value of about 5 billion years, plus or minus 1.5 billion years, a number that is in agreement with the age of the solar system derived from the age of meteorites. So apparently all the bodies of the solar system formed at about the same time, some 4.6 billion years ago. So you can add this as the final item to your list of characteristic properties of the solar system. The challenge for modern planetary scientists is to compare the characteristics of the solar system with predictions of solar nebula theory so they can work out details of how planets formed. Everything astronomers know about the solar system and star formation suggests that a solar nebula was a fragment of interstellar gas cloud. Such a cloud would have been mostly hydrogen with some helium and small amounts of heavier elements. That is precisely what you see in the composition of the Sun. Analysis of the solar spectrum shows that the Sun is mostly hydrogen, with a quarter of its mass being helium and only about 2% being heavier elements. Of course, nuclear reactions have fused some hydrogen into helium, but this happens in the Sun's core and has not affected the composition of its surface and atmosphere, which are the parts you can observe directly. That means the composition revealed in the Sun's spectrum is essentially the composition of the gases from which the Sun formed. This must have been the composition of the solar nebula, and you can also see that composition reflected in the chemical compositions of the planets. The inner planets are composed of rock and metal, and the outer planets are rich in low-density gases such as hydrogen and helium. The chemical composition of Jupiter resembles the composition of the Sun. But if you allowed low-density gas to escape from a blob of stuff with the same overall composition as the Sun or Jupiter, the relative proportions of the remaining heavier elements would resemble the chemical composition of Earth and the other terrestrial planets. An important clue to understanding the process that converted a solar nebula gas into solid matter is the variation in density among solar system objects. You have already noted that the four inner planets are small and have high densities, resembling Earth, whereas the outermost planets are large and have low density, resembling Jupiter. Even among the four terrestrial planets, you will find a pattern of slight differences in density. Merely listing the observed densities of the terrestrial planets does not reveal the pattern clearly because Earth and Venus, being more massive, have stronger gravity and have squeezed their interiors to higher densities. The uncompressed densities, the densities the planets would have if the gravity did not compress them, or to put it another way, the average densities of the original construction materials, can be calculated using the actual densities and masses of each planet. In general, the closer a planet is to the Sun, the higher its uncompressed density. So here we can see Mercury. So here we can see its observed density and its observed density and compressed density. According to the solar nebula theory, the observed pattern of planet densities originated when solid grains first formed, a process called condensation. Solid particles condense from the gas of the nebula as it cooled. The kind of matter that could condense in a peculiar region depended on the temperature of the gas there. In the inner regions close to the Sun, the temperature was evidently 1500 Kelvin or so. The only materials that can form grains at that temperatures are compounds with high melting points, such as metal oxides and pure metals, which are very dense. Further out in the nebula, it was cooler, and silicates, a rocky material, could also condense. In addition to metal, these are less dense than metal oxides and metals. Mercury, Venus, Earth, and Mars are evidently composed of a mixture of metals, metal oxides, and silicates, with proportionality more metals close to the Sun and more silicates further from the Sun. Even further from the Sun, there is a boundary called the ice line, beyond which water vapor could freeze to form ice particles. Yet a little further from the Sun, compounds such as methane and ammonia could condense to form other types of ice. Water vapor, methane, and ammonia were abundant in the solar nebula. So beyond the ice line, the nebula would have been filled with a blizzard of ice particles, mixed with some amounts of silicates and metal particles that could also condense there. Those ices are low-density materials. The densities of Jupiter and other planets correspond to a mix of ices, plus relatively small amounts of silicates and metals. The sequence in which the different materials condense from the gas as you move away from the Sun towards the low temperature is called the condensation sequence. It suggests that the planets forming at different distances from the Sun should have accumulated from different kinds of materials in a predictable way. People who have read a little bit about the region or the origin of the solar system may hold the common misconception that a matter in a solar nebula was sorted by density, with the heavy rock and metal sinking towards the Sun and the low density gases being blown outward. That is not the case. The chemical composition of the solar nebula was originally roughly the same throughout the disk. The important factor was temperature. The inner nebula was hot and only metals and rock could condense there, whereas the cold outer nebula could form lots of ices along with metals and rock. The ice line seems to have been between Mars and Jupiter, and it separates the region for formation of the high-density terrestrial planets from that of the low-density Jovian planets. In the development of the planets from the material of the solar nebula disk, Three processes operated to collect solid bits of matter, metal, rock, ice, into larger bodies called planetesimals, which evidently made up planets. The study of planet building is the study of these three processes. In a previous section, you learned a little bit about the process of condensation. Planetary development in the solar nebula began with the formation of dust grains by condensation. A particle grows by condensation when it adds matter one atom or molecule at a time from a surrounding gas. Snowflakes, for example, grow by condensation in Earth's atmosphere. In a solar nebula, dust grains would have been bombarded continuously by atoms of gas, and some of those stuck to the grains. Microscopic grain capturing a layer of gas molecules on its surface increases its mass by a much larger fraction than a gigantic boulder capturing a single layer of molecules. For that reason, condensation can increase the mass of a small grain rapidly. But as the grain grows larger, condensation becomes less effective and other processes become more important. So before we continue, do you guys want a small break or do you want to continue with the lecture? Okay, so it seems like the majority of you wants a small break. So let's take a small break and we will continue the class at 6:50.
So what is my favorite TV show? That is a really, really good question. So I usually like all sci-fi stuff. So yes, Star Trek is one of my favorites, but it depends on which Star Trek series. But I enjoy all Star Trek series, but my favorite Star Trek series is The Next Generation. It's basically anything sci-fi. I love fantasy shows as well. And I also like thrillers and horrors. So yes, I enjoy the new Star Trek series as well. So I still need to watch Star Trek Picard. I haven't gotten around to that yet. So welcome back. How was your chemistry test? So yes, I've watched Space Force on Netflix, and that was brilliant. No, I haven't watched The Man Who Fell from Earth. So yes, it's a good. I will watch it. That's good to get the chemistry test doing quite alright. So I've tried anime, but I can't seem to get into anime. They are. I hope Death Note is apparently good. Dragon Ball Z I've watched. But recently I've discovered a series Slasher on Netflix, and that's quite good. So now with this, continuing with our so to watch Rick and Morty. Yes, I've watched Rick and Morty. That is brilliant. So remember, let's continue with the lecture. So with the formation of planetesimals, it is important to note that condensation is the first step. The next step is accretion. So the second process of planetesimal formation is accretion, the sticking together of solid particles. You may have seen accretion in action if you have walked through a snowstorm with big fluffy flakes. If you caught one of those flakes on your glove and looked closely, you saw that it was actually made out of many tiny individual flakes that had collided as they fell and accreted to form larger particles. In a solar nebula, the dust grains were, on average, no more than a few centimeters apart, so they collided frequently and could accrete into larger particles. So, just on a different note, my two favorite shows of all time was probably Breaking Bad and House of Cards. When the particles grew to sizes larger than a centimeter, they would have been subject to new processes that tended to concentrating. One important effect was that the growing solid objects would have collected into the plane of the solar nebula. Small dust grains could not fall into the plane because the turbulent motions of the gas kept them stirred up. But larger objects, more mass, and gas motions could not have prevented them from settling into the plane of the spinning nebula. Astronomers calculate this would have concentrated the larger solid particles into a relatively thin layer about 0.01 AU thick that would have made further growth more rapid. There is also no clear distinction between a very large grain and a very small planetesimal. But you might consider an object to be planetesimal when its diameter approaches 1 kilometer or so. So what do the planetesimals look like? You get a clue from this photo of the 5-kilometer wide nucleus of Comet Wild. However rocky or icy, the planetesimals must have been small, irregular bodies scattered by craters from collisions with other planetesimals. This concentration of large particles and planetesimals into the plane of the nebula has some resemblance to the flattening of the forming galaxy. And a process also found in galaxies may have become important once the plane of planetesimals formed. Computer models show that the rotating disk of particles should have been gravitationally unstable and would have been disturbed by spiral density waves resembling the much larger ones found in spiral galaxies. Those waves could have further concentrated the planetesimals and helped the coalescence into objects up to 100 kilometers in diameter. Through these processes, according to the solar nebula theory, the disk of gas and dust around the forming sun became filled with trillions of solid particles ranging in the size of pebbles to tiny planets. As the largest began to exceed 100 kilometers in diameter, a third process began to affect them, and a new stage of planet building began, the formation of protoplanets. So remember, we started with condensation, then accretion, and now it's the formation of protoplanets. So the coalescence of planetesimals eventually formed protoplanets, and a name for massive objects destined to become planets. As these larger bodies grew, a new process helped them grow faster and alter their physical structure. If planetesimals had collided at orbital velocities, they would have been unable to stick together. The typical orbital velocity in a solar system is about 10 kilometers per second. Head-on collisions at this velocity would vaporize the material. However, the planetesimals were all moving in the same direction in a nebular plane and didn't collide head-on. Instead, they merely rubbed shoulders, to speak, at low relative velocities. Such gentle collisions would have been more likely to combine planetesimals than to shatter them. The largest planetesimals would grow the fastest because they had the strongest gravitational field. A stronger gravity could attract additional material. Their gravity could also hold on to a cushioning layer of soil that would trap fragments. Astronomers calculate that the largest planetesimals would have grown quickly to protoplanetary dimensions, sweeping up more and more material. Protoplanets had to begin growing by accumulating solid material because they did not have enough gravity to capture and hold large amounts of gas. In the warm solar nebula, the atoms and molecules of gas were traveling at velocities much larger than the escape velocities of most Mars-sized protoplanets. Therefore, in their early development, the protoplanets could grow only by attracting solid bits of rock, metal, and ice. Once a protoplanet approaches a size of 15 Earth masses or so, however, it could begin to grow by gravitational collapse, the rapid accumulation of large amounts of infalling gas from the nebula. The theory of protoplanet growth into planets supposes that all the planetesimals had about the same chemical composition. The planetesimals accumulated to form a planet-sized ball of material with homogeneous composition throughout. Once the planet formed, heat would begin to accumulate in its interior from the decay of short-lived radioactive elements. The violent impacts of infalling particles would also have released energy called heat of formation. These two heating sources would eventually have melted the planet and allowed it to differentiate. Differentiation is the separation of material according to density. Once a planet melted, the heavy metals such as iron and nickel plus elements chemically attracted to them would settle to the core, while the lighter silicates and related materials floated to the surface to form a low-density crust. The scenario of planetesimals combining into planets that subsequently differentiate is shown in figure 15.8. So here we can see it. Planetesimals contain both rock and metal. A planet grows to uniform planetesimals. The resulting planet of homogeneous composition, then heat from radioactive decay and planetesimal infill causes differentiation. And finally, the resulting planet has a metal core and low density crust. The process of differentiation depends partly on the presence of short-lived radioactive elements whose rapid decay would have released enough heat to melt the interior of planets. Astronomers know such radioactive elements were present because very old rock from meteorites contained daughter isotopes such as magnesium-26. That isotope is produced by the decay of aluminium-26 with a half-life of 0.74 million years. The aluminium-26 and similar short-lived radioactive isotopes are gone now, but they must have been produced in a supernova explosion that occurred shortly before the formation of the solar nebula. In fact, some astronomers suspect that a supernova explosion could have triggered the formation of the Sun and other stars by compressing interstellar clouds. This our solar system may exist because of a supernova explosion that occurred about 4.6 billion years ago. Why are you guys so afraid of differentiation? Differentiation is not that bad. You mustn't think about math and calculus as math and calculus, but you have to think about it rather as a language. And how do you learn a language? You practice a language, and that is the language the universe speaks. Yeah, proofs is horrible. I don't know why lecturers ask proofs. I have the opinion that if you see a proof, you've seen a proof. You don't need to know a proof to get through the course. You need to understand how to do differentiation on a damn proof, but I know there's other lecturers that won't agree with me. So the work is fun, but sometimes the lecturers try to confuse us. I know that feeling. Physics, math is actually really fun. It's real world math instead of axioms. That's true. So I have a toxic relationship with math. Couples therapy didn't help. I can't escape her. She follows me. No, math is fun. And wait until you do applied mathematics, where you do a lot more fun work, such as setting up your differential form of equations. So something I'm considering one day. So usually when you speak about your children, the boyfriend or girlfriend has to do a certain task to be eligible to date your children. So I was thinking for someone to be able to date my children one day, when I have children, is they should be able to solve a differential equation at least. That would be my test. If planets formed by accretion of planetesimals and were later melted by radioactive decay and heat of formation, the Earth's early atmosphere may have consisted of a combination of gases delivered by planetesimal impacts and released from a planet's interior during differentiation. The creation of a planetary atmosphere from a planet's interior is called outgassing. Given the location of Earth in a solar nebula, planetary scientists calculate that gases released from its interior during differentiation would not have included as much water as Earth has now. So astronomers hypothesized that some of Earth's water and atmosphere accumulated late in the formation of the planet as Earth swept up volatile-rich planetesimals. These icy planetesimals would have formed in the cool outer parts of the solar nebula and could have been scattered towards the terrestrial planets by encounters of the Jovian planets, creating a comet bombardment. According to the solar nebula theory, the Jovian planets could begin growing by the same process that built the terrestrial planets. However, in an inner solar nebula, only metals and silicates could form solids. So the terrestrial planets grew slowly. In contrast, the outer solar nebula contained not just solid bits of metals and silicates, but also ices that included plentiful hydrogen. Astronomers calculate that the Jovian planets would have grown faster than the terrestrial planets and quickly became massive enough to begin even faster growth by gravitational collapse, drawing in large amounts of gas from a solar nebula. The terrestrial planet zone did not include ice particles, so those planets developed relatively slow and never became massive enough to grow further by gravitational collapse. The Jovian planets must have reached their present size and no more than about 10 million years. Before the Sun became hot and luminous enough to blow away the remaining gas in the solar nebula, removing the raw material for further Jovian growth. As you will learn in the next section, disturbances from outside the forming solar system may have reduced the time available for Jovian planet formation even more severely. The terrestrial planets, in comparison, grew from solids and not from the gas, so they could have continued to grow by accretion from solid debris left behind after the gas was removed. Mathematical models indicate that the terrestrial planets were at least half finished within 10 million years, but could have continued to grow for another 20 million years or so. The solar nebula theory has been successful in explaining the formation of the solar system, but there are some problems, and the Jovian planets are the troublemakers. New information about star formation process makes it hard to explain the formation of the Jovian parents. This has caused astronomers to expand and revise the theory of planet formation. So here in this image, we can see an image of Jupiter made by the Cassini spacecraft as it flew by on the way to Saturn. And a shadow of the moon is visible near the left limb. Jovian worlds pose a problem for astronomers investigating the origin of planets. Planet-forming nebula are blown away in only a few million years by nearby luminous stars. So Jovian planets must form more quickly than initial calculations predicted. Newer research suggests that accretion followed by gravitational collapse can build Jovian planets in about 1 million years. Under certain conditions, direct gravitational collapse may form some large planets in just thousands of years. The new information is that gas and dust disks around newborn stars don't last long. You've seen images of dusty gas disks around the young stars in the Orion star-forming region. Those disks are being evaporated by intense ultraviolet radiation from the hot ONB stars forming nearby. Astronomers have calculated that nearly all stars form in clusters containing ONB stars, so this evaporation may happen to most disks. Even if a disk did not evaporate quickly, the gravitational influence of the crowded stars in a cluster could strip away the outer parts of the disk. Those are troublesome observations because they seem to indicate that disks can't last longer than about 10 million years and may evaporate within an astronomical very short span of 100,000 years or so. That's not long enough to grow a Jovian planet by the combination of condensation, accretion, and gravitational collapse proposed in the standard solar nebula theory. Yet Jovian planets are common. In the final section of this chapter, you will see evidence that astronomers have found planets orbiting other stars. And almost all the planets discovered so far have the mass of Jovian planets. There may also be many terrestrial planets orbiting those stars that are too small to be detected at present. But an important point is that there are lots of Jovian planets around. How they can form quickly enough before the disks of raw material evaporate is referred to the Jovian problem. So, are there any protoplanets near Sun-like stars? Yes, there are, and we're going to discuss that as well. So, there are actually quite a lot that has been discovered. And that is why those planets are being investigated to see if we cannot detect perhaps other life or some form of life on those planets. But yes, we are going to discuss that in depth as well. Mathematical models of the solar nebula have been produced using specially built computers running programs that take weeks to finish a calculation. The results showed that a rotating gas and dust of the solar nebula could have become unstable and formed Jovian planets by skipping straight to the step of gravitational collapse. That is, massive planets may be able to form by direct collapse of gas without first forming a dense core by condensation and accretion of solid material. Jupiters and Saturns can form in these direct collapse models in only a few thousand years. If the Jovian planets formed in this way, they could have formed before the solar nebula disappeared, even if the nebula was eroded quickly by neighboring massive hot stars. So why don't I believe in Planet 9? Because there's not evidence for it, and we cannot detect it. And without any evidence, it cannot exist. What evidence, Mr. Melville? So far, the math doesn't show there's anything, and our observations show there isn't anything. So I will watch this, but you shouldn't believe anything and everything that's on YouTube. The original solar nebula theory hypothesized that the planets formed by accreting a core and then, if they became massive enough, accelerated growth by gravitational collapse. The proposed modification to the theory suggests that the outer planets could have skipped the core accretion phase. Now, you have learned enough to put all the pieces of the puzzle together and explain the distinguished characteristics of the solar system. The disk shape of the solar system is inherited from the motion of material in the solar nebula. Sun, planets, and moons mostly revolve and rotate in the same direction because they formed from the same rotating gas cloud. The orbits of the planets lie in the same plane because the rotating solar nebula collapsed into a disk, and the planets form in that disk. The solar nebula hypothesis is evolutionary in that it calls on a continuing process to gradually build the planets. To explain the odd rotations of Venus and Uranus, however, you may need to consider catastrophic events. Uranus rotates on its side. This might have been caused by an off-center collision with a massive planetesimal when a planet was nearly formed, or by gravitational interactions with Saturn and Jupiter. Two hypotheses have been proposed to explain the backward rotation of Venus. Theoretical models suggest that the Sun produced tides in the thick atmosphere of Venus that could have eventually reversed the planet's rotation. An evolutionary hypothesis. It also is possible that the rotation of Venus was altered by an off-center impact late in the planet's formation. And that is a catastrophic hypothesis. Both may be true. The second item in the table is the division of the planets into terrestrial and Jovian worlds. Can be understood through the condensation sequence. The terrestrial planets formed in the inner part of the solar nebula, where the temperature was high and only substances such as silicates and metals could condense to form solid particles. That produced the small dense terrestrial planets. In contrast, the Jovian planets formed in the outer solar nebula, where the lower temperature allowed the gas to form large amounts of ices. That allowed the Jovian planets to grow rapidly and become massive, low-density worlds. Also, Jupiter and Saturn are so massive they were able to grow by drawing cool gas by gravitational collapse from a solar nebula. The terrestrial planets could not do this because they never became massive enough. The heat of formation, that is, the energy released by infalling matter, was tremendous for these massive planets. Jupiter must have grown hot enough to glow with a luminosity of about 1% that of the present Sun. Although it never got hot enough to generate nuclear energy as a star would, nevertheless, Jupiter is still hot inside. In fact, both Jupiter and Saturn radiate more heat than they absorb from the Sun, so they are evidently still cooling. At a glance at a solar system suggests that you should expect to find a planet between Mars and Jupiter. At that present location is the asteroid belt. Mathematical models indicate that the reason asteroids are there rather than in a planet is that Jupiter grew into such a massive body that it was able to gravitationally disturb the motion of nearby planetesimals. The bodies that could have formed a planet just inward from Jupiter's orbit instead collided at high speeds and shattered rather than combining, were thrown into the Sun or were ejected from the solar system. The asteroids seen today are the last remains of those rocky planetesimals. So at the beginning of this chapter, shows a planetary system observed around another star that also has an asteroid belt just inward of the Jovian mass planet. Perhaps that asteroid belt was produced in the same way as ours. The comets, in contrast, are evidently the last of the icy planetesimals. Some may have formed in the outer solar nebula behind Neptune, but many probably formed among the Jovian planets where ices could condense easily. Mathematical models showed that the massive Jovian planets could have ejected some of these icy planetesimals into the far outer solar system. In a later chapter, you will see evidence that some comets are icy bodies coming from those distant locations, falling back into the inner solar system. The icy Kuiper belt objects appear to be ancient planetesimals that formed in the outer solar system but were never incorporated into a planet. They orbit slowly far from the light and warmth of the Sun and, except for occasional collisions, have not changed much since the solar system was young. The gravitational influence of the planets deflects some Kuiper belt objects into the inner solar system, where they are also seen as comets. The large satellite systems of the Jovian worlds may contain two kinds of moons. Some moons may have formed in orbit around forming planets in a miniature version of the solar nebula. Some of the smaller moons, in contrast, may be captured planetesimals, asteroids and comets. The large masses of the Jovian planets would have made it easier for them to capture satellites. In table 15.1, you noted that all 4 Jovian worlds have ring systems. And you can understand this by considering the large mass of these worlds and their remote locations in the solar system. A large mass makes it easier for a planet to hold on orbiting ring particles, and being further from the Sun, the ring particles are not as quickly swept away by radiation pressure and a solar wind. It is hardly surprising then that terrestrial planets, low-mass worlds located near the Sun, have no planetary rings. The last entry in the table is the common ages of solar system bodies, and the solar nebula theory has no difficulty explaining that characteristic. According to the theory, the planets formed at the same time as the Sun and should have roughly the same age. So, ladies and gentlemen, our time is up. So let's end tonight's lecture here. So in tomorrow night's lecture, we will continue clearing the nebula. In the first 10 minutes of the class, I will also discuss the memo of the 2 quizzes that we've done so far. If you have no questions, then you are more than welcome to log off. I will see you all in tomorrow night's class. If you have tests due this week or assignments, good luck with the preparation and good luck with the tests and exams. Have a wonderful evening, and I will see you all tomorrow. I will be on campus tomorrow from 9:30 to about 2:30. Otherwise, have a great evening. I will remain active for another minute or 2 if you have questions. I will watch the video, Mr. Melville. So if there's no further questions, then I'm also going to log off. Okay, so one question. On one of my days taking pictures of the moon, it was cloudy, but I was able to see the moon slightly earlier that day. So can I use a sketch for that day instead? Yes, you are more than welcome to. So if there's no further questions, then I'm also going to log off. So have a great evening, everyone, and see you all tomorrow.